In this video, we're going to calculate how many photons a laser will emit if that laser is emitting a wavelength of 365 nanometers. It does that in 100 milliseconds and with a power of 276 milliwatts. So we have three different units here. We have nanometers, milliseconds, and milliwatts. So the first we want to do is get those into their base units. So we want to get this into meters, we want to get this into seconds, and then this into watts. It will make the math much easier later on. So let's first start with those nanometers. So we have 365 nanometers. We're going to multiply that by for every 1 meter. We have 1 times 10 to the 9 nanometers. That's going to give us our 3.65 times 10 to the minus 7 meters. Let's move on to our milliseconds. So for 100 milliseconds, we're going to multiply that by for 1 second, we have 1,000 milliseconds. So we're going to have 0.100 seconds. And then finally for our milliwatts, we have 276 milliwatts. We'll multiply that by our 1 watt over 1,000 milliwatts. That's going to give 0.276 watts. Now that we have these in their base units, are going to be much easier to use. So now let's start to plug in some of the equations that we need. So the first is going to be energy is equal to power times time. Now energy is going to be, the units will be joules, power will be joules per second, and time will be in seconds. Hence why we converted our milliseconds into seconds. So now we can plug these things in. So our energy is going to be equal to our power. We know that's 276 milliwatts or 0.276 watts. And just as a forward, joules per second is the same as equal to watts. So we'll also put that here, or joules per second. So we have our 276 instead of watts. Let's make it easy. Let's call that joules per second. And we're going to multiply that by our time, which is 0.100 seconds. This will then make it a little bit easier when it comes to our units. Since our seconds are here and on the bottom of this fraction, they're going to cancel each other out, leaving us only with joules, which is exactly what we want for our energy term. So our energy is going to be equal to 0.0276 joules. All right, now that we have our energy, now we can start to get closer to our photons by using the following equation, where energy is equal to our Planck's constant, which is h, our speed of light, which is c, our lambda, which is wavelength, and n, which is our number of photons. So we now have every single, everything to solve except for our n. So let's plug in our values. So we have our energy, which is 0.0276 joules. That's going to be equal to h, which is Planck's constant, which is 6.626 times 10 to the minus 34. Those units are joules times seconds. We then have our speed of light, which is 3.00 times 10 to the 8. That's going to be meters times per second. And we're going to divide all of that by our wavelength, which we saw for up above, which is 3.65 times 10 to the minus 7 meters. We still have our n, which is our number of photons. So if we move things around and solve for n, if we look at our units, we're going to have our seconds and per seconds. Those are going to cancel each other out. We have our meters on top and our meters on bottom. So those are going to cancel out. And then we're going to have our joules here and our joules here. In the end, they will cancel each other out, leaving us with no units, which is good since we're looking for a number of photons. So our n, number of photons, is going to be equal to 5.07 times 10 to the 16, and we'll call that photons. So first, convert all of your different units into their base units. meters, seconds, watts, or in this case joules per second. Then solve for energy right here, which then allows you to plug that into our final equation right here, and then solve for our number of photons n.